Hello student, I am Dr. S.L. Munde, Assistant Professor, Department of Mathematics, Sri RLT College of Science, Akola. Dear student, in previous lecture we have seen Cauchy inequality, or we can say that Cauchy estimate theorem. Also we have seen some problems on Cauchy inequality or Cauchy estimate. So in this lecture we will see next point, that is entire function and Liouvilles theorem. So before going to see the proof of the Liouvilles theorem, we will see the entire function definition. What is the entire function? What is the entire function? So entire function means if the function f is a defined and analytic on a whole complex plane C. Okay, generally we take the complex plane C in region G. Okay, in region G on whole complex plane C. So let us suppose that the function f may be the function of z, f of z may f of z. The function f is said to be a entire, but when if that function is defined and analytic on a whole complex plane C is called as a entire function. That is, f c is defined and analytic in a whole complex plane C. Okay, so that function is called as the entire function. Okay, so what are the entire functions? For examples, exponential function is an entire function, and for example f of z equal to e raised to power z, and where z is lies between in a complex plane C. So every polynomial function is an entire function. Polynomial function is also entire function. Okay. Then third, f of z, z upon z minus a, where z is not equal to 3, is not an entire function. Okay, because this is not a defined and not an analytic function. Okay, so therefore the third function is not an entire function. Okay, for z is not equal to 3. Okay, now we will see the theorem, that is Liouvilles theorem. So this Liouvilles theorem is also important exam point of view. So what is the statement of the Liouvilles theorem? Okay, so let us suppose that f is a bounded entire function, then f is a constant function. Okay, suppose that f of z is a bounded entire function, then we have to prove that f of z is a constant function. Okay, so this is the simple statement of the Liouvilles theorem. There may be the question in examination, state and prove Liouvilles theorem. Okay, so this is the statement of the Liouvilles theorem. If f of z is the entire bounded function, then it is a constant function. So let us see the proof of this theorem. So what is given? We have given f be the function which is defined and analytic on a complex plane C, because already given that entire function f is a entire function. So therefore we can say that the given function f be a function which is defined and analytic on a complex plane C, because f is a entire function given that. Okay, so let us to prove this theorem. So let us be fixed any point z in a complex plane C. So to prove this theorem, let us we take any point z in a complex plane C and take a radius r greater than 0, such that open ball whose center z radius r which is containing in complex plane C. So let us suppose that, so this is the whole complex plane C. Okay, and this is a inner circle whose center is z and radius is r. Okay, open circle. Inner circle means open circle. So here f of z is a entire function. That means f of z is defined and analytic on a whole complex plane C. Okay. So let us suppose that z be the any point in a complex plane C which containing close in open circle whose center is z and radius r. So r is greater than 0. Okay. So therefore we can say that f is analytic in a open circle whose center is z and radius r, because this circle which is containing in a complex plane C. Okay, and on a complex plane C, f of z is an analytic function. So therefore we can say that f of z is an analytic function in this circle, in open circle. Okay, so which implies, or we can say that therefore f of z or f is bounded on a complex plane C, okay, which is already given in a question. Okay, analytic means that is a bounded function. So therefore f is bounded on a open circle whose center z and r. Okay, if f of z is bounded on a whole complex plane C, then we can say that f is also bounded on a on a this open circle whose center is z is and radius r. Okay, so therefore by Cauchy inequality there exists a capital M greater than 0 such that mod f of z less than equal to capital M. So for every z belongs to C. So here curve is gamma of t equal to z plus r because z is a center and a radius is a capital R e raised to power it, where t lies between 0 to 2 pi. So therefore by using Cauchy inequality we can prove this theorem. Okay. So therefore by Cauchy equality or Cauchy estimate, f n of z equal to less than equal to n factorial into capital M upon r raised to power n. Okay. So for the n equal to 1, let us we see mod f dash of z equal to less than equal to capital M upon r, where n equal to 1, 1 factor means 1. Okay. So, but we have given f is a entire function, means that is analytic on a whole complex plane C. Okay, but actually we have given f is a entire function, that means we can say that that function f is a analytic function on a whole complex plane C. Okay, so here let us we choose r as a large. So taking limit r tends to infinity. So taking limit r tends to infinity on both sides, we get limit r tends to infinity mod f dash of z less than equal to r tends to limit r tends to infinity m upon r. So taking the limit r tends to infinity, we get m by infinity, and m by infinity means less than equal to 0. Okay. So mod f dash of z less than equal to 0. Okay. Also we can prove that mod f dash of z greater than equal to 0. Okay. So from equation number 1 and 2 we can say that, so this is also true for mod f dash of z greater than equal to 0. Now from equation number 1 and 2 we can say that mod f dash of z equal to 0. So that is f dash of z equal to 0. So taking integration on both sides, we can say that f of z is a constant function. So therefore here f of z is a constant function. Okay, so this is the complete proof of the Liouvilles theorem. Okay, so now we will see some examples on a Liouvilles theorem. So what is the first example? First example is given as, show that f of z equal to sin z where z belongs to C is not a bounded or a unbounded function. Okay, so we have to show that so f of z is a bounded, is not a bounded, or we can say that unbounded function. Okay, so what is the proof? Suppose that f of z equal to sin z where z belongs to C be a bounded function. Okay, so let us we consider this f of z is a bounded function. Okay, but we know that f of z equal to sin z is an analytic function. We know that the every trigonometric function is an analytic function because that function is a differentiable function. So f of z sin z is a differentiable function. Hence, you can say that this function is an analytic function. So we know that f of z equal to sin z is an analytic function, and also it is an entire and bounded function. So by using Liouvilles theorem, we can say that this function is an analytic function, and therefore we can say that this function is an entire and bounded function. So therefore by using Liouvilles theorem, f of z equal to sin z is a constant function. Okay. So therefore by using the Liouvilles theorem, we can say that f of z equal to sin z is a constant function, and it is a contradiction to the our assumption. Okay. What was the our assumption? We have assumed f of z equal to sin z is a bounded function, but we got f of z equal to sin z is a constant function, and this is a contradiction to our the assumption, and thus our assumption f of z is a bounded function is a wrong, and hence we can say that f of z is a not a bounded, or we can say that f of z is a unbounded function. Okay, so this is the simple example on a Liouvilles theorem. Now we will see the another example on a Liouvilles theorem. Show that f of z equal to cos z, where z belongs to C, is not a bounded or show that unbounded function. So this example we will show by the contradiction method. Okay. So let us suppose that f of z equal to cos z, where z belongs to C, be a bounded function. Let us suppose that f of z equal to cos z is a bounded function. Okay. But we know that this f of z cos z is an analytic function, because f of z is a this function is a differentiable function. So therefore we can say that f of z equal to cos z, where z belongs to C, is an analytic function. An analytic function, we can say that is an entire function and bounded function. So therefore by using the Liouvilles theorem, okay, by using the Liouvilles theorem, f of z equal to cos z is a constant function, and this is the contradiction to our assumption. Okay, so what was our assumption? Our assumption was f of z cos z is a bounded function, but we got f of z equal to cos z is a constant function. Okay, so this is the strictly contradiction to our assumption, and hence we can say that our assumption is wrong. F of z cos z is a bounded function is wrong, and hence we can say that f of z is not a bounded function, or we can say that f of z is a unbounded function. Okay, so this is the second example on a Liouvilles theorem. Okay, so in this lecture we have seen one theorem, that is the Liouvilles theorem, which is depends on a entire function definition. Okay, so entire function definition, and we have seen Liouvilles theorem, and also we have seen two problems on a Liouvilles theorem. Okay, so in next lecture we will see the next point. Okay.